In the digital age, software systems are the engines of modern enterprise. From social media platforms connecting billions to e-commerce sites processing millions of transactions, their reach is vast. Yet, for every success story, there are countless services that failed to grow. The reason often lies not in the idea or the initial code, but in the foundational decisions made long before the first user ever logged on. At the heart of this challenge is a concept known as scalability, a principle that determines whether a software application can gracefully handle growth or will collapse under its own success. This is the story of system design and architecture, the invisible blueprints that dictate the fate of our digital world. Understanding these concepts is not just a technical exercise. It is fundamental to grasping why some software scales and why so much of it fails. The terms system design and system architecture are frequently used interchangeably, but they represent distinct, though related, layers of planning. System architecture is the high-level, strategic blueprint. It defines the core components of a system, such as the databases, the application servers, the user interfaces, and the messaging queues, and it dictates the fundamental principles and patterns that govern how they interact. Architecture is concerned with the what and the why. It answers questions like, what are the major structural elements? What are the non-functional requirements, such as security, reliability, and performance? It sets the constraints and foundational rules for the entire project. Much like an urban planner decides the layout of a city's main roads, zoning laws, and public utilities, it is a conceptual map that is difficult and costly to change once construction has begun. System design, on the other hand, is the more tactical, detailed implementation of that architectural vision. It is the how. If architecture decides that the city needs a public transport system, system design determines the specific bus routes, the type of trains to be used, the location of the stations, and the ticketing mechanism. In software, this translates to choosing specific technologies, defining the precise application programming interfaces, or APIs, between services, structuring the database schemas, and planning the network topology. System design is the process of making concrete choices to fulfill the abstract requirements laid out by the architecture. A robust architecture provides the framework for effective design, but it is the combination of both that creates a system capable of enduring real-world pressures. When a software system is first built, it is often designed for a small, predictable number of users. The initial architecture might be a monolith, where the entire application, the user interface, business logic, and data access layer is contained within a single, unified codebase and runs as a single process. For a startup or a small project, this approach is fast to develop and easy to deploy. However, this simplicity masks a critical vulnerability. As the number of users grows, from hundreds to thousands, and then to millions, this monolithic structure begins to strain. Poorly planned architecture, which fails to anticipate this growth, becomes a bottleneck. Every request, whether it's loading a user profile, processing a payment, or running a search query, competes for the same limited computational resources, the same CPU, the same memory, and the same database connections. The symptoms of this strain manifest in ways that are frustratingly familiar to users. The first sign is often a noticeable slowdown. Response times, which were once instantaneous, now take several seconds as the server struggles to keep up with the volume of requests. Soon, the system becomes unstable. During peak traffic periods, the server may become so overwhelmed that it crashes, rendering the service completely unavailable. These outages can become more frequent and longer in duration. In the worst-case scenarios, the strain on the data layer can lead to data corruption or even permanent data loss, as the database fails to write information correctly under heavy load. This is not just a technical failure, it is a business failure. A service that is slow, unreliable, and loses user data will quickly lose user trust, and ultimately, its user base. The initial, elegant simplicity of the monolithic architecture becomes its fatal flaw. To solve the problem of a single server being overwhelmed, engineers employ a strategy known as load balancing. A load balancer is a specialized server or service that acts as a traffic controller for the system. Instead of all user requests hitting a single application server, they first arrive at the load balancer. Its job is to distribute these incoming requests evenly across a pool of multiple identical servers. This strategy is central to horizontal scaling, a method of increasing capacity by adding more machines to the system, as opposed to vertical scaling, which involves making a single machine more powerful. If one server can handle 1,000 concurrent users, 10 servers, managed by a load balancer, can theoretically handle 10,000. This allows the system's capacity to grow in direct proportion to user demand. For horizontal scaling to be effective, however, the application servers themselves must be designed in a specific way. They need to be stateless. A stateful service is one that stores user-specific data, or state, in its local memory from one request to the next. For example, it might remember a user's shopping cart contents. The problem with this approach is that it tethers a user to a specific server. If the load balancer sends that user's next request to a different server in the pool, that new server will have no knowledge of the shopping cart, leading to a broken user experience. In contrast, a stateless service treats every request as a brand new interaction. It does not store any session data locally. Instead, session state is externalized, stored in a shared location accessible to all servers, such as a distributed cache or a central database. This design decouples the user from any single machine, allowing the load balancer to freely route requests to any available server. This freedom is the key to achieving true elasticity and fault tolerance. While stateless application servers are a critical component of scalability, the database often remains the most significant bottleneck. In a traditional monolithic system, a single, large relational database serves all the application's needs. As the volume of data and the rate of read and write operations increase, the single database becomes the central point of failure, much like the single application server did. Vertically scaling the database server by adding more CPU, RAM, and faster storage can only go so far, and becomes prohibitively expensive. The architectural solution is to move from a monolithic database to a distributed data storage strategy. This can involve several patterns. One is database sharding, where data is horizontally partitioned across multiple database servers. For instance, users with last names A through M might be stored on one database, while users N through Z are stored on another. Another approach, often used in microservices architectures, is to give each service its own private database, optimized for its specific needs. A user profile service might use a document database, while a financial transaction service might rely on a transactional SQL database. This distribution of data storage eliminates the single point of failure and allows different parts of the system to scale independently. The history of the tech industry is filled with examples that illustrate this principle. Early social media platforms that were slow to break apart their monolithic databases struggled with frequent, highly publicized outages. In contrast, companies like Netflix and Amazon, which pioneered the move to distributed microservices and highly available distributed databases, were able to achieve massive, global scale. Their success was not accidental. It was the direct result of architectural decisions that prioritize scalability and resilience from the beginning. This leads to a final, crucial principle. System design and architecture must be a primary consideration, preceding any significant coding effort. In the rush to build a product and get to market, there is a powerful temptation to skip the planning phase and jump directly into implementation. This is often a short-sighted and costly mistake. Building software without a solid architectural plan is like constructing a skyscraper without a blueprint. The initial floors may go up quickly, but the structure will lack the foundation to support its own weight as it grows taller. Sooner or later, fundamental flaws will be discovered. Retrofitting a poorly designed system for scalability is an immensely difficult, expensive, and time-consuming process. It often requires a complete rewrite of the application, all while the existing, failing system must be kept running. This kind of open-heart surgery on a live system is fraught with risk and can stall a company's growth for months or even years. Some never recover. Therefore, the most important work in building a scalable system is done before a single line of application code is written. It involves careful analysis of business requirements, a deep understanding of potential growth vectors, and the deliberate creation of an architectural framework that is flexible, resilient, and built to last. It is in these early decisions that the difference between sustained growth and catastrophic failure is ultimately decided. Please subscribe to the channel for more documentaries like this.